On this video, we will talk about the symmetry of polar equations. So let's start by looking at this function on the right hand side. Notice that it says the graph of the function for sine, so let's just highlight that, is shown to the right. Now, does this graph appears to have some kind of a line of symmetry? But notice that it seems like this graph seems to have a line of symmetry over what can be seen as the y-axis, which again, we're not going to call it the y-axis because notice like here we're talking about polar equations, so therefore we only have either r or theta. How do I know that this seems to be a symmetry? Well, notice that if I take a look at this half of a function, imagine yourself that you're getting this half and you reflect it, is definitely going to overlap with the other half of the function. So it seems like this function for sine of theta is symmetric over this line, which looks like to be the y-axis, which again, it is not the y-axis. In this case, the way that we're going to be define this line is by saying the angle pi over 2. Because notice that this line can be represented as whenever the angle is equivalent to pi over 2. Because if I choose any point on this line, this point, it can be seen as 1 over pi over 2, because it is exactly 1 unit away, and the angle is pi over 2. Notice that if I would have chosen this point right here, that would be equivalent to 1, 2, 3, comma, pi over 2. Notice that if I would have chosen this point over here, that would have been negative 2 comma pi over 2. So notice that it doesn't matter which point I choose on this line that is vertical. There's one thing that all those points have in common, and that is their angle is equivalent to pi over 2. So that would be negative 4 over pi over 2. So that's why a vertical line, or at least this vertical line, it's going to be defined as whenever the angle is equivalent to pi over 2. So notice that there might be some functions which that will be symmetric over certain lines. And our first example is that we can have a symmetry over the line angle equals pi over 2. But what are other lines of symmetry that we might encounter whenever we're dealing with polar equations? Well, there are three types of symmetries that we will encounter whenever we're taking a look at polar equations, and we're going to talk about them now. So the first type of symmetry that we can encounter is the one that we did on the introduction question, which is a line of symmetry with respect to the line pi over 2. So in this case, this is the line of symmetry that we're referring to, pi over 2. Now, let's think about the results. So let's choose a point. Let's choose this point, and let's define this point as r comma theta. Now, if we were to reflect this point over the line theta equals pi over 2, then if I get this point and I reflect it, it should land somewhere over here. Like take this point, reflect it, it should land someplace over here. So now the question is, what is the exact coordinate of my image in relation to the original point, r comma theta? Well, notice that this point right here, if I define this point, instead of calling it r comma theta, I define a point that it's going on the negative direction as negative theta, and still using the same distance. Notice that this point right here can be seen as r comma negative theta. Convince yourself that this is true. So this is the original point that we have. But now I'm saying, well, what if instead of going at a positive degree, I go into a negative degree, but still conserving the length of r? So that would be exactly right here. So that would be r comma negative theta. And now it just so happens that now if I get this point and I define it, and now instead of going in a positive direction, I go on a negative direction, therefore negative r comma negative theta, we will always get the image of a point that is reflected over the line theta equals pi over 2. So therefore, the image of any point that is reflected over the line pi over 2, the image will always be defined as negative r negative theta. So we have the above symmetry, and if we replace r theta with negative r negative theta, it gives the same equation. So in other words, the image of a curve reflected over the line theta equals pi over 2, it will always have the coordinate points negative r negative theta. So now another type of symmetry that we could have gotten is something that we call a symmetry with respect to the polar axis. Now the polar axis, you can think about it as just the x-axis. And now we're going to try to do the same. So if we've been given a point, and if I reflect it over the quote-unquote x-axis, which in reality we're going to call it the polar axis, I know that my point is going to be landing somewhere over here. So somewhere over here, if I get this point and I reflect over this line, it's going to land somewhere here. So now my question is, can I define this point in terms of the original point? Well, notice that if I reflect this point over this line, whatever angles of degrees that I gotten here, all that's going to happen is that I'm just going to go in a negative direction. So therefore, my new point, we still conserve in the same length of r, because the distance of the point doesn't really change towards the origin. The only thing that changes is that now, instead of calling it positive theta, I want to call it negative theta. And this is pretty much going to be the image of any point that is reflected over the polar axis. So we have the above symmetry. If we replace r theta with r comma negative theta, so any point that is reflected over the polar axis, the image, it's always going to be defined as r comma negative theta. The third type of symmetry that we do have when it comes to polar coordinates is the symmetry that we call with respect to the pole. Now, what do we mean by the pole? Well, the pole, in some sense, is the origin, or whenever my line theta equals pi over 2 and the polar axis intersect exactly at the origin. But what do we mean by reflecting a point over a point? All that this means, at least in the context of polar coordinates, is if you have a point that is being defined as r comma theta, if you reflect that point over what is called the pole, all it's going to do is it's just going to change its direction. Therefore, my image is going to be defined as negative r comma theta, because we're still using the same angle here. But now, instead of going towards the point, by reflecting a point over the pole, all it does is, instead of going towards the original point, it's just going to go against. So therefore, we have a negative r. So we have the above symmetry if we replace r theta with negative r comma theta. And it gives the same equation. So far, all we have done is we have just summarized, or we have introduced the idea of three lines of symmetry, or three ideas of symmetry. We have three symmetries whenever we have a line over theta equals pi over 2. And that symmetry is going to be given by any given point. If I reflect it over the line pi over 2, my image is always going to be defined as negative r negative theta. if I would reflect it over the polar axis, any point after its reflection, the image is going to be defined as r comma negative pi. And any point, if I reflect it over the pole, the image, it's always going to be defined as negative r comma pi. I'm sorry, theta. Let's actually put this into practice. So let's determine the symmetry of the equation r equals 4 sine of pi. I mean, one way that we can see it is we could graph this function and see what the image gives us. But let's actually do it using the three concepts that we just discussed a couple seconds ago. So let's test some symmetry. Let's test to see if this equation is reflective over the line theta equals pi over 2. So to test the symmetry, all we got to do is see if it makes a true statement. Well, I know that if my equation is reflected over the line pi over 2, if I plug in these values, negative r comma negative theta, and it gets me the original equation back, then it must have been symmetric over the line. So we're going to test that. So to test to see if this equation is reflective over or symmetric over the line pi over 2, I'm going to replace r with negative r. And I'm going to replace theta with negative theta. And I'm going to see, well, is this going to give me the same equation as the original, which is 4 sine? Well, let's see. Negative r is negative r. But now, notice that here we have sine of negative theta. But recall that sine, it's an odd function. Where recall that odd means that if I take the sine of a negative angle, that's equivalent to the negative of the same angle. So therefore, this expression, since I know that sine is odd, now this is equivalent to 4 sine of positive theta. And now notice I have a negative on the left and negative on the right. In other words, they will cancel out. And now I have r equals sine of theta. But now notice that by plugging these values, negative r comma negative theta, I get the original equation back. So therefore, the equation for sine of theta, it's definitely symmetric over the line theta equals pi over 2. Because by plugging in our result, we get the same original equation back. But now let's test to see if the same equation is reflected over the polar axis. How do we see if it's reflected over the polar axis? Well, I'm going to plug in my image and I'm going to see if I get the same original equation back. So it says I'm going to get my equation, and at r, I'm going to substitute with a positive r, so that doesn't change anything. And I'm going to get 4 sine. But now it's saying that theta, I should replace it with negative theta. And now let's see if this is true. Well, we have r equals, and again, notice that sine, it's an odd function. So therefore, the sine of a negative angle is the negative of the sine of that angle. So we have negative 4 sine of that angle. And now notice that our result, it doesn't give us the same original equation back. So therefore, this equation, 4 sine of theta, it is not reflective or reflexive or symmetric, I'm sorry. So this equation, it is not symmetric over the polar axis. So the last thing that we have to test is see if the same equation is symmetric over the pole. And again, we're going to get our original equation. And now to test to see if it's symmetric over the pole, we're going to replace an r with a negative r. And we're going to replace a theta with the positive theta. And now notice that there's nothing else that we can do to this equation. And now this equation is definitely not the same as the original. So therefore, our conclusion is that it is not symmetrical, or not, it's not symmetric over the pole. Now let's just graph our function to show that, yes, indeed, it does follow our analysis that we just did here. Our analysis, it's saying that if I graph the function for sine of theta, it's only going to be reflected over the line theta equals pi over 2. So notice that here we have graphed the function for sine of theta. This is our function now. And one thing that you will notice is that it seems to only be reflective over the line pi over 2. And that's the same conclusion that we obtain algebraically. Let's do one more example. Let's just do one more example here. So now under example 2, it states the graph of the right is given by this equation, r equals 3 plus 2 cosine of theta. And now what we want to do is we want to complete the following graph using the symmetry of the function. So this is kind of like a piece of a graph, and now we want to complete the actual graph. But in order for us to see, well, if I want to complete it, I need to see what's my line of symmetry. So the first thing that we want to do is identify, is this function symmetrical over a line? Well, we're going to do the same test. We're going to test to see if it's symmetrical over the line pi over 2. And again, to test symmetry over the line theta equals pi over 2, all we got to do is plug in the values of negative r, negative theta, and see if it gives me the same equation back. So let's do that. So here we have our function, and now I'm going to substitute r with negative r, and I'm going to substitute theta with negative theta, because this is how we test our points. And now let's see if anything, let's see if it gives me the same equation back. So negative r is negative r, 3 plus 2. But now notice that cosine, remember that cosine is an even function, which states that the cosine of a negative angle, that's equivalent to just the cosine of that same angle in a positive value. So therefore now cosine of negative theta, this is just equivalent to the cosine of a positive theta, and there's nothing else that we can do to this function. So now notice that by plugging in the values negative r, negative theta, I don't get the same equation or the original equation back. So therefore, this function is not symmetrical over the line theta equals pi over 2. Okay, so we still got 2 more lines and points to test. So now let's test over the polar axis. And again, to test the polar axis, we're going to get our original equation, and we're going to substitute it with r comma negative theta and see if that gives us the same original equation back. So we're going to get our function now, and I'm going to substitute with positive r with the positive r, and theta with negative theta. So now we're going to get the following. But now again, notice that here we have cosine of a negative angle, and I know that cosine is even. So therefore now this becomes 3 plus 2 cosine of a positive. And now notice that my result matches the original equation that was given to us. So therefore, the equation, it is symmetrical over the polar axis. And now the last thing that we need to test is, well, is it symmetrical over the pole? And recall that in order to test to see if the function is symmetrical over the pole, all we gotta do is replace the original equation with negative r and theta and see if it gives me the same original equation back. So let's do that. We're going to get our original equation, and I'm going to substitute r with negative r, and I'm going to substitute theta with positive theta because that's what our conclusion was saying. And at this point, notice that there's nothing else that we can do to this function. There's no other type of manipulation that we can do when it comes to the sign. So we don't have the same equation back. So therefore, it is not symmetrical over the pole. So the only conclusion that we got here is that this equation that we just defined here, it's only symmetrical over the polar axis. We recall that the polar axis is exactly this. This is the polar axis. So therefore, if this is half of the function and I want to complete this graph, all I gotta do is just get every point and try to reflect it over this line. So let's get this point and let's reflect it over the polar axis. So notice that this point is 1, 2, 3 units away from the origin. So therefore, if I get this point and I reflect it, it should still be under the same degree, but now it's just going to be 1, 2, 3. All right, let's choose another point. Let's choose this point right here, which is exactly 1, 2, 3, 4 lines of openness to the left, and exactly 1, 2, 3, 4 units away. So we're going to do the same. So 1, 2, 3, 4, and over this line, I'm going to count 1, 2, 3, 4. So here we have another point. So if I get this point and I reflect it over this line, it's going to land somewhere over here. Let's just choose another point. I want to choose this point, which seems to be about one line of openness and exactly being 1, 2, 3, 4, 5. So one line of openness to the opposite direction in 1, 2, 3, 4, 5. So exactly right here. Let's just get one more point. Let's get this point right here, which is going to be 1, 2, 3, 4 line of openness and exactly 2 units away from the origin. So we're going to get about 1, 2, 3, 4 line of openness and 1, 2 units away. And I feel like at this point we can complete the graph, because if we connect those points, we should have gotten something like this. And notice that all I did is just, we're doing a sketch because we're going to learn how to do the actual graph of a function on our next lesson. But right now we're just sketching, just using the idea of knowing that it's symmetrical over the polar axis. Now let's just double check to see if this is actually the function that we wanted to have. Let's see. Now let's just graph the function 3 plus 2 cosine of theta. So r equals 3 plus 2 cosine of theta. Notice that this is exactly. So notice that we were given half of the function, and we knew that it was reflected over the polar axis. So we just reflect the points, and now notice that the complete function, it's exactly what we got in here. Well, this is a rough sketch, but it's a good indicator as to see how the function should look like. So this is just how we can use the line of symmetry. We can use the line of symmetry to properly finish up some of the graphs whenever an incomplete graph is given. And this is the 3 main ideas. We got 3 types of symmetry. Over a line, that equals pi over 2. And the way that we test to see if it's symmetrical is by replacing negative r with negative n negative theta. And we get the same original function. Then we know it's symmetrical. For polar axis, we substitute r and negative theta. And with respect to the pole, we substitute negative r, positive theta.